Hello everyone! Today I'm excited to talk to you about Gelato Relay, a powerful solution that can dramatically improve the user experience of your decentralized applications. If you ever struggled with onboarding new users to your dApp because they need to acquire native tokens just to pay for gas, or if you want to provide a truly gasless experience for your users, this presentation is for you. We'll cover what relaying is, how it works, and most importantly, the security considerations you need to be aware of when deploying it in your applications. Now let's look at the specific onboarding problem of a crypto user. First, a user that's looking to join your protocol needs to open an account at a centralized exchange, go through KYC, buy crypto with fiat currency, transfer it to their wallet, and then they can use your dApp. This process can take hours to days. So new crypto users that are coming in are going to have this type of onboarding experience. Now let's take a look at relays. With relays, users sign a transaction off-chain, and a relayer sends the transaction on their behalf, paying for the cost of the transaction. This essentially removes the friction that is currently present when requiring gas fees for users. So how do relays actually work? Well, first, the user signs a message. This happens entirely off-chain using their wallet like MetaMask. There's no gas cost for signing a message. It's just a cryptographic signature proving that they own their private key. Next is that the relayer verifies. This is where Gelato comes in. The relayer receives the signed message, verifies the signature is valid, and matches the claimed user addresses and validates that the request hasn't been tampered with. Finally, the relayer executes the transaction on-chain. The relayer constructs and sends the actual transaction, and the relayer pays the gas fee up front. This flow enables gasless transactions while maintaining security through cryptographic signatures. The user's signature proves they authorized this action, even though someone else sent the transaction. This is what is known as a meta transaction, where it's a regular Ethereum transaction that contains another transaction within itself. So now what is a meta transaction? Now you might be wondering, if the relayer sends the transaction, how does the actual user's intent get to the target contract? Well, a meta transaction is essentially a transaction within a transaction. Look at this visual representation. The outer transaction is sent by the relayer to the Gelato Relay contract on-chain. Inside that transaction, there's an inner transaction, the actual message that needs to be delivered to your target contract. So the flow is, the relayer initiates the outer transaction, sends it to the Gelato Relay contract. The Gelato Relay receives it, validates everything, and then forwards the inner transaction to your target contract. Your contract then executes the intended action. This nested structure allows the user's signed message to be safely wrapped and transported on-chain by a third party, while preserving the ability to verify who the real user is. It's like sending a letter inside a secure envelope. The postal service, which is the relayer, delivers it, but the letter inside the user's intent remains intact and verifiable. Now let's look at EIP-712 signatures. EIP-712 provides a standardized signing of typed structured data. This means that the user signs a clear human-readable message that specifies exactly what they are authorizing. So when a user signs a message with their wallet, there's no gas cost for signing and no chain interaction needed at this stage. The signature is then verified on-chain by the relayer. So what's in a signed message? Well, it contains critical information. So in short, EIP-712 signatures are the cryptographic foundation that makes secure gasless transactions possible. Without them, there would be no way to prove the user authorized the relayed transaction. Now let's take a look at ERC-2771. There's two different approaches for validating signatures. So on the left, a non-ERC-2771, you'll need to build a custom authentication. So you need your own signature verification system. You need to manually verify signatures. The message.sender is always the relayer, so you lose visibility on who the real user is. Your security implementation will be complex and you'll have higher vulnerability risk because you're essentially building your own authentication system from scratch. On the right, the ERC-2771 approach, you get built-in signature verification that's been tested by thousands of projects. You get a standardized authentication using a proving pattern. You can access the real user's address through the underscore message sender function. It's easy to implement. You just inherit a contract and replace message.sender with underscore message sender. And most importantly, it's battle tested security. So non-ERC-2771 requires you to become a cryptography expert and build your own secure authentication. ERC-2771 gives you production-ready security out of the box. So why should you use ERC-2771? Well, the message.sender is the relayer. How do you verify who initiated the request? Well, in this case, ERC-2771 encodes the user address in the call data and provides underscore message sender to decode it. Now let's take a look at the code. Our smart contract inherits from the ERC-2771 context. The key is the constructor parameter trusted forwarder. This is Gelato's relay address on your network. The contract trusts transactions coming from this address. Look at line 44 in the increment function. Instead of using message.sender, we use underscore message sender. When Gelato relays the transaction, the last 20 bytes of the call data contain the original user's address. ERC-2771 context extracts it, so underscore message sender returns the actual user and not Gelato's address. Our contract stores each action in a history array with the user address, previous value, new value, message, and timestamp. This proves the contract knows who the real user is. We use Foundry for smart contract deployment. The deployment script is super simple. It reads the trusted forwarder address based on the chain ID. So this is Sepolia testnets trusted forwarder, and this is Zircuit mainnets trusted forwarder. This information can be found in the Gelato docs. The front end uses WAGMI for wallet connection and VM for blockchain interactions. We have a custom hook called useCounter that handles all the relay logic. When a user clicks increment, we encode the function call, create an ERC-2771 request, and send it through Gelato Relay's sponsored call ERC-2771 method. The user only signs the message, completely free. Gelato handles the rest. Now that we're done looking at this contract, let's actually deploy it. Cool. Now let's grab the contract address, and we'll paste it into our env file. Now we need to get our Gelato Relay API key. You can navigate to the Gelato application, go to API keys, get started. We'll name ours Gelato Relay. Once that's created, make sure to go to the policy page and select the specific network that you want to sponsor transactions from. We can select sponsor all transactions or the specific contract address that we want. So in this case, let's use the contract address that we've created, navigate back to the platform, and enter the custom ABI for it. We can specifically allow certain smart contract functions. So for example, incrementing would remain gasless, but decrementing and resetting would require a gas fee. Now that we created our API key and set the permissions, now coming to the actual gas tank, I previously sent a transaction depositing some amount of ETH to the gas tank. Let's copy our API key and paste it into our end file. Let's navigate to the front end. Now, if we take a look at our wallet, we can see that although we have testnet ETH on Garfield, we don't have any ETH on Sepolia. If we click increment, we can sign this. It'll be sent, forwarded to Gelato Relay. We will get a hash. If we go back, we can see that the counter has updated. If we click decrement, we made too many requests, so we need to wait a little bit. And we get an error message because decrementing will cost gas for the user. We can, of course, adjust this over on the application side. We can enable all transactions. Then we can come back, and then we can decrement. Let's try disabling sponsorships now. And as you can see, this request failed. Now, one more key critical component to implementing gasless transactions. We've talked a lot about ERC-2771 and the security that it provides, but there's one thing that I want to mention. ERC-2771 plus delegate call equals danger. So if you use ERC-2771 with any function that uses delegate call, especially when using a multi-call contract, you must avoid this combination or implement it very carefully. So what's the vulnerability? When delegate call is used to call the contract itself, the execution context is preserved. This means message.sender remains as the Gelato Relay contract. Here's where it gets dangerous. Attackers can append victim addresses to the call data they control. So when underscore message sender extracts those last 20 bytes, it gets the victim's address that the attacker put there, not the actual signer. The contract then thinks the victim authorized the action, and the attacker can impersonate them. So in short, using ERC-2771 with delegate call can allow an attacker to impersonate any address, which then can lead to significant problems, especially when those that require access control or access to different funds. Hopefully you learned what relays are and how to use them. Thanks for watching, and leave your comments down below.